me share the screen. Recording. Where are we now? Can you see? Can you see my screen or not?
Can Doctor.
Can thank you. So now we are going to calculate the tooth tip height, the WTP, and also the tooth end height. Height means the Indiana. So where is the WTP and WTE? So this is the WTP and this is the WTE. So again, when you want to find the relationship, first of all, we need to apply VA. So the first thing, we already know this VA. And then we need to know where is the flux flow through. So this is the part that we want to know. And also, we also need to know the VA in this part. This one we don't want, because all the fluxes flow through here will go to here. We go to here. Okay, so and then a portion of the flux from the permanent magnet enter a tooth hole through WX surface. This is what the meaning. A portion of the fluxes flow through here. And then across the tooth tip height, WTP. So it flows through this one and then go to here. Then as well, go through here and then go to here. Go through here and then go to here. Go through here and go to here. So this is the so-called part of it. Therefore, the total flux crossing the tooth tip height flux S is expressed as VA equals to VA. So BA is a BG times WX from LA. So let's take a look. So between the BG here is times WX times LA. And then equals to B saturation times WTT and then times LA. So between B saturation, this one B saturation is B saturation TT, tooth tip, and AX. Later we'll explain. We go to the left hand side first. Left hand side from the equation of 6, so we just copy down. BG we already calculated, LA we already obtained. Now we want to find the WX. So how to find WX? Assuming this part, assuming this part is a 2D. Okay, and then we have too small, too big. Now we have this WTB. We have a WX. Okay, so first of all, we need to find the jari. S equals to 2 pi RSI. This is RSI. Which means this one, Then we want to divide by how many slots? We have a 12 slot, so we divide by 12, which means it's 2 pi RSI divide of number of slots. And then this length will be total length here. And then we minus WTB. We already calculated. We minus WTB that we already calculated. And then we divided by 2. We divided by 2. We divide by 2. Then we will find our WX. So that's why 2 pi RSI divide by number of slots minus WTB. And then divide by 2. So this is our WX. Then substitute all the value, we find this is the flux X. After that, the flux saturation level in the tooth tip region is slightly lower, which is a B set 1.6 Tesla. Okay. We need to assume that B set TP here, it cannot go to 1.6 Tesla. All the fluxes going through here. Because the area here is very small. It is too small until it cannot fit on 1.6 Tesla. So usually what we think is about 1 Tesla. So 1 Tesla. So this is our B set TP and then WTP times LA. So now we want to find WTP, we just use pi x divided by this 2, and and then we get 2.7540. And then we will choose the nearest 0.5 value, which means 3 mm. So WTT chosen here will be 3 mm. Now this will be 3 mm. Okay, and then the dimension of tooth end is normally set between 0.8 to 2 lah. Also, we can be calculated by divide by 2. So usually I just calculated and divide by 2 lah. Which means if let's say this is our 3 mm, if let's say we want to find WTE, we just use 3 mm divide by 2. That's it. Huh? So next, what is that? Done. So the radius of the bottom slot and also the RT, outer radius of the slot opening. Okay. Maybe how to. Okay. So radius of the bottom slot is this one. Now this is the area that we want to slot our winding, and then usually we use this line we call as a bottom, and then this will be our top or outer. Oh, that's why you say outer radius of the slot opening. Then the radius of the bottom, how to use it, how to calculate it. Just now we already know the RSO. Okay, we already know the RSO, and then we calculated, we found that WSY. So we just use RSO minus WSY, we will get RSB. Same as well here. If let's say we want to find RT, we will use RSI plus WTT. This is the RSI, then we plus the height here, then we will get our RT. All of this value you need to use in your mini project. So same, then we found this one. So we will get the RSB, we will get the RT. Okay, next we will need to go to the rotor pole. Rotor pole. First of all, we need to understand what is inside lah. So the flux path. This one is a flux per pole pitch. Per pole pitch. Pole pitch means angle of one magnet. For example, now have a north pole, south pole, north pole. So the pole pitch can be here, can be here, can be here. The pole pitch is the angle of the magnet. For example, if let's say we have a two-pole machine, right? We have two-pole machine. This is north pole, this is south pole. So what is a pole pitch? 180, right? Because it's a 360 divided by 2 pole, which is 180 mechanical degree. Mechanical degree is geometry 1, which means in the space. Okay, pole pitch. So what is the flux per pole pitch? How it flows? When it goes, south pole will go in, north pole will go out. South pole go in, north pole go out. So go in like this. Go in like this. It will split into 2 lah, it split into 2. Then what variable we have? LA, we already know that. R shaft means the radius of the shaft. RR means the radius of the inner rotor. Rn is the radius of the magnet. ARY means area of the rotor yoke. This part we call rotor yoke, rotor back iron. And then APM is the area of the permanent magnet. So this is the area of the permanent magnet. Okay. And then what else? So now we want to calculate the easiest first. RM, RR, WRY, and R sharp. RM. So RM is where? RM is this one. Okay. Just now we know that the RSI already have it, and then we know the air gap between each LG given 1 mm. So what we know, how we want to calculate RM? We use RSI minus 1 mm, then we will have a RM. Then we also know that the thickness of the HM is a 3 mm. So we use Rm minus thickness, then we will get the RR. So this is the equation. Then we found 26 and 23. So from figure 2, the total flux per pole pitch produced by an arbitrary. Arbitrary means random. random magnetic pole, either south pole, either north pole. For instance, the south pole is separated into two paths, passing through the rotor-yoke area ARY and going to the adjacent magnet, the north pole. So the total flux per pole pitched across the magnet surface APN can be calculated like this. So now we want to find what? We want to find the rotor-yoke, the width of the rotor-yoke. We want to find the width of the rotor-yoke. Where is it? This one. So how to relate it is a VA here will be equals to VA here. Okay? So VA for the permanent magnet equals to VA for the rotor-yoke. Permanent magnet we use VG. APM is a W PM times LA. Then rotor-yoke we use a saturation of the iron steel. ARY is W RY times LA. So this is the thing that we want to find. This is given. I mean calculated. Then WPM we also need to calculate lah. That one is very easy because we only use 2 pi Rm divided by how many poles? Let's say we have the jari, okay, Rm divided by, let's say 10 pole, so we divide by 10. So this is the WPM. So if let's say we calculate this one, we have this one, we have this one, we have this one, we have this one, then we can get our WRY. So come back to here, Vg times area of the permanent magnet, Vg times 2 pi Rm divided by number of poles, and then times La. So we get this value. After that, because the flux per pole is the 2 times of this. Why it is 2 times? This one is wrong. Because I forgot to divide by 2. This is only one part. So I forgot about this part. I must use 2 here. Okay? That's why this is flux per pole. But when it comes to the rotor-yoke side, the rotor-yoke is flux per pole divided by 2. Something like this. Okay? That's why the total flux per pole is the 2 times of the rotor-yoke side. And then we do some pushing, then we get the rotor-yoke, which is about 4.23, then 4.5. So if let's say we already calculated the rotor-yoke, we want to find the R shaft, we just use RR minus rotor-yoke. Okay, RR minus rotor-yoke. But this time, a little bit different because the value that we need to choose must be smaller and even number. So for example, R shaft calculated, we use 23 minus 4.5, which is this one. Then we have 18.5. First, we cannot choose 19 or 20, cannot bigger, or else this part will become smaller. We cannot choose bigger side for R shaft like this. But then this part will become smaller. When it becomes smaller, saturation will happen. Okay? So we need to choose smaller, which is either 18, 17, 16. And then we need to choose the nearest even number. So the nearest even number is 18. So we use 18. So the chosen must be the nearest smaller even number. So for example, if let's say our WRY chosen is 4.5, then our R shaft calculator is used 23 minus 4.5, it is 18.5. And the nearest smallest even number, it can be 18, 17, 16, 15, 14, macam. So we need to choose the smallest even number, which is 18. So the chosen will be 18. If let's say the calculator value for RY chosen is 5.5. Let's say here is 5.5. So we use 23 minus 5.5, we have a 17.5. So the number that we can choose is 17, 16, 15, and 14. So the nearest smallest even number will be 16. So we choose 16. Let's say our calculated value here is 6.5. Okay? Then we use 23 minus 6.5, we have 16.5. So the nearest smallest value is 16, 15, 14, and so on. So the nearest one is 16. So we will go to 16. Let's say the calculated value is 7.5. After deduction, we have 15.5. The chosen value will be 15, 14, 13, and so on. And then the smallest even nearest, the smaller even number, nearest even number is 14. So we will choose 14. Okay? So sum of the project is less than 0 or R sharp is 2 mm. Please contact me. Please contact me. So again, we need to go. Okay, any question? Any question? Any question?
No, sir.
No,
No,
sir.
Okay, thank you. No question. I'll proceed. So after that, we need to calculate the other parameter lah. I mean, we need to know what is the wire we need to put. Let me think. How many things we need to go? Oh, a lot of things. Maybe this will be next class one. Should we stop actually? Or continue? Should we stop or continue? We still can accept. Hello? Stop for. Oh, okay. Then we will stop first. We'll stop lah.